Hi guys, this is your video on limits that are going to infinity. If you had watched the optional video that I posted on, was that Friday? I think it was Friday. I talked about like your preview for this session. So let's get right into it. So this is technically section 12.4. I know you don't really probably care about that, but that's okay. This is section 12.4, limits going to infinity. So before we do that, I want you to recall for just a second. Imagine if you had, back when we did polynomials, and I might have, some function looks like this. Well, you hopefully remember that this polynomial could be a cubic, or something higher. So it could be a fifth or seventh or a ninth degree, but it has to be an odd degree. And we would talk about the end behavior. And the way that we talked about the end behavior on polynomials like this, I would say as x heads to negative infinity, y is heading to negative infinity. And as x is heading to positive infinity, y is heading to positive infinity. And that just basically meant that on the left side of the graph, you were going down, and on the right side of the graph, your end behavior was going up. Or, back when you were in Algebra 2, your teacher might have just said, just write down, up. I always harped on this notation because I know that this is pre-calculus and I want you guys to be as prepared as possible for calculus. So that was coming when we talked about limits. So that's kind of what limits that go to infinity, that's kind of what they're about. So for example, let's say that I had a polynomial function. I said maybe I'll take the limit as x is heading towards infinity of, maybe I'll take a cubic function like x cubed plus 1. Okay, so graphically speaking, if I looked at this cubic function, x cubed plus 1, so the stuff that you'd have to remember about that is, all right, if this is a function, f of x equals x cubed plus 1, helps when you remember what your parent functions look like. So my parent function would be a cubic function with a vertical shift up 1 unit. So it would look something like this. And really, when I ask as x goes to infinity, I'm really asking about what's happening on the right-hand side of that graph. So when x gets really, really big on this side of the graph, my y values are going to keep getting bigger and bigger and bigger. So technically, I could say that this limit is heading to infinity because I see that on the right-hand side of the graph, we are going up. Now, when we've talked about limits in this unit, hopefully you have picked that up, that when limits don't go to a specific value, the limit doesn't exist. So anytime you say that my limit is heading to an infinite number, you can always say that the limit does not exist because we are not heading to a specific number. Okay? All right, so I could give you something like the parent function 1 over x. So we'll take the limit of the parent function 1 over x. And maybe I'll say as x is heading to infinity. Alrighty, so that would be, again, I'm just going to focus my attention on the 1 over x piece for a second. So if I'm thinking about that as a function, that'd be like, y equals 1 over x, or f of x equals 1 over x. And it's helpful to remember what those rational functions look like, especially the parent one. So you have a horizontal asymptote and you have a vertical asymptote. And your graph would look something kind of like this. The third quadrant and the first quadrant. So again, if I'm asking you here, as x goes to infinity, I'm technically asking about the right-hand side of your graph for end behavior. So I want x to go forever towards the right. So where are my y values going? That's what limits do. So where are my y values heading? Well, my y values are getting closer and closer to that horizontal asymptote. So in this particular problem, my values are heading to a number, and they are heading to the y asymptote, which is at 0, so they're heading to y values of 0. So that would be my limit for this one. And actually, if I had asked about the limit of 1 over x, I don't want an or here, we'll just say this is another example, side by side with it. So if I had said the limit of 1 over x, and I said as x is going towards negative infinity, well, that just means that now I'm going to get rid of this. I'm going to head off to the right-hand side of, or excuse me, the left-hand side of my graph, because my x values are going to get more and more negative this way. And what's my graph doing? Well, my graph is getting, oops, sorry, not sure what that did. My graph is getting more and more horizontal, heading towards that horizontal asymptote. It's doing it from negative y values, but that's okay, because our limits aren't about necessarily how you get there. It's just where are you heading, and my y values are getting closer and closer and closer to a y value of 0. So, oh my gosh, what is happening? To a y value of 0. Sorry about my technology. So anyway, so whether you go to the left-hand side of the graph or whether you go to the right-hand side of the graph, limits going to infinity are really just end behavior. So where are you going as you head towards negative or positive infinity? So let me kind of get you into how I kind of think about it. So just remember that limits as x approaches infinity of some function, or as x approaches negative infinity of some function, is the same thing as end behavior. So I need you to kind of get that into your brain sooner than later, because that helps sometimes with your ability to answer a limit question that involves a limit going to infinity. So a limit as x just heads to infinity, or as x heads to negative infinity, it's the exact same logic or exact same mindset as end behavior. So if you're heading, if x is going to positive infinity, it's end behavior on the right-hand side of the graph. If x is going to negative infinity, it's end behavior on the left-hand side of the graph. So the way that I think about it, remember, well, let's take the limit as x goes to infinity. Of 4 minus 3 over x squared. All right, so you have to kind of keep in mind all of those properties of limits that we also talked about. So those properties of limits would be things like I can split up this limit into 2 limits. So another way that I could think of this as the limit as x approaches infinity of 4, and then minus the limit as x approaches infinity of 3 over x squared. So you can kind of split this up into 2 different, mindsets there. Now, on the first one, this is just a horizontal line of y equals 4, right? So no matter where I'm going to give a little break there just so that way you don't mess up the 4. But no matter what happens, as I head out to infinity, so that's right-hand behavior, so I'm just going to keep going this direction, y is always at 4. So that first one will always be 4 no matter what. Now I need to evaluate this second limit. So that was me evaluating this first guy to 4. Let me evaluate this second guy to what it's going to be. Okay, so the second one, if you think about your parent function, that's fine. I mean, thinking about or if you want to go to the graph, you can always go to the graph. The parent function would have been like 1 over x squared. So if you take it back to 1 over x squared, that would have looked like this. And the only difference between 1 over x squared and 3 over x squared is that we've really just done a vertical stretch by a factor of 3. So the picture doesn't really change a ton. So if you're letting x go off to infinity, my y values are getting closer and closer to that horizontal asymptote of 0. Now, a lot of people like to think about that whole, remember my first approach for evaluating a limit is to substitute in the value if you can. But the problem is when you're plugging in infinity, you can't really plug in infinity because it's not a number. I'm gonna actually like bring myself back up here. It's not actually a, let me put it up here. It's not actually a number. It's a it's a destination. It's a location. So I'm going to say plug in infinity, quote unquote, but you don't actually plug in infinity. I mean, you do, but you don't. Like you kind of think in your brain, let me just kind of plug in infinity and see what happens. So if I had gone back up here, so sorry, this limit comes out to be 4 minus 0, which is 4. That's the answer to this problem. I guess I should have finished that first. All right, so if I came back up here to the beginning and I had said, well, let me kind of take that same approach and let me plug in infinity, even though it's not a number. Really, you can't substitute in things that aren't numbers, really, but I'm going to do it anyway. So 4 minus 3 over, and I'm going to think about that infinity value. It's really an infinity squared. So whether you'd have infinity squared or you don't have infinity squared, this is really like 4 minus 3 over. Infinity squared is still an infinite number, still an infinite, like you're heading to an infinite value. So 3, this thing right here, and if you also remember when we did slant asymptotes, when we were dealing with rational functions, 3 divided by a really, 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 really big number. Like, I mean, this is 3 over 1,000, 3 over 1,000,000, 3 over 1,000,000,000. That is a number that is really, really, really close to 0. And the bigger that number gets, the faster that this thing, let me find a different color here, the faster that this thing, oh, I like that better anyway, the faster that this thing gets to 0. So with that in mind, this whole thing is still going to be heading to 4 minus 0, which means that limit is 4, either way you think about it. So split it up using your properties of limits or quote unquote plug in infinity. All right, now your turn to try one. All righty. Evaluate the limit as x approaches infinity, or we could do negative infinity, doesn't really matter. We'll say of 6 plus 2 over x. Okay, how'd you do? I don't know what approach you want to take. I'm going to take the approach of just quote unquote plugging. I'm going to take you back there. I'm going to plug in infinity, even though it's not really a number, so you really shouldn't plug it in, but I'm going to do it anyway. So that means I'm going to, right here for x, have that infinite value. So this will give me 6 plus 2 divided by infinity. Whoops. Sorry, I like it to stay 100% in case you want to see these later. So 6 plus 2 divided by infinity. And when we think about these values right here, 2 divided by a very, 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 very big number means that this thing right here is heading to 0 as we are talking about infinity, which means that this limit is really equal to 6 plus 2 divided by infinity is 0, which means that this limit would just be 6. Okay, so you're probably thinking, wow, that's actually really easy. I mean, it kind of is. If we stick with, rational functions and stuff that we know, they're really not bad. So let's recall, actually, before we do this, let's recall what you remember about rational functions. So when it comes to rational functions, I would always ask you about horizontal asymptotes or slant asymptotes at times. So we would have, of course, we had vertical asymptotes, and that's whatever, makes your values undefined in the denominator. But let's remember horizontal asymptotes and slant asymptotes. So first, let's remind ourselves what they looked like. Keep going back to that pretty pink highlighter, I like it. All right, so a horizontal asymptote, of course, is a horizontal line at whatever value you came up with. So let's say I have a horizontal asymptote, like say y equals 3. Okay, so if I have a horizontal asymptote at y equals 3, and then maybe I have a vertical asymptote, we'll say at x equals 0, my rational function could look something like this, especially if it's just like the parent function shifted up. So if that's what I've got, then if I let x go to infinity on the right-hand side of the graph, the y values are just getting closer and closer to that horizontal asymptote. Or if I let x go to negative infinity on the left-hand side of the graph, those y values are getting closer and closer and closer to that horizontal asymptote. So really, when it comes to rational functions, if you had a horizontal asymptote, then your end behavior is going to be heading to that horizontal asymptote. If you had a slant asymptote, remember a slant asymptote is just like it sounds. You had the degree of the top is 1 larger than the degree of the bottom, which we're about to go over. And let's say we had a slant asymptote that came up something like this. And maybe I have a vertical asymptote, you know, right here again. Then your graph might have looked something like this. Go off towards it. You can never cross a vertical asymptote, remember, ever, never, never. But slant asymptotes and horizontal asymptotes, you can cross. And the reason why you can cross them is because those asymptotes are just, as x gets bigger and bigger and bigger, y just kind of levels off to this line. As y gets smaller and smaller, or excuse me, as x gets smaller and smaller and smaller, your graph just heads off towards that slanted line. So in this particular case, on the right-hand side of the graph, the y values are heading to infinity, and on the left-hand side of the graph, the y values are heading to negative infinity. So that would be a situation where you could say that your limit doesn't exist. So let's take that and apply it with some rational functions. What if I have something like the limit as x approaches infinity of, say, negative 2x plus 3 over 3x squared plus 1. Okay, so you have to remember, how did you get those horizontal asymptotes? How did you know that you had a horizontal asymptote? So there was 3 things you had to look at. If you had a horizontal asymptote, the degree of your numerator was smaller than the degree of your denominator. And if that happened, then you had a horizontal asymptote of y equals 0. If the degree of your numerator was equal to the degree of your denominator, then you had a horizontal asymptote of y equals that leading coefficient over that leading coefficient. And if the degree of your numerator was bigger than the degree of your denominator, then you had no horizontal asymptote. And that was all for horizontal asymptotes. When it came to a slant asymptote, you only had a slant asymptote if the degree of your numerator was bigger than the degree of your denominator by 1. And if you had a slant asymptote, then your limit still wouldn't exist anyway because you're heading off to infinite values. So keeping that in mind, I look at this one. I'm ignoring the limit for just a second. So just pretend like that limit isn't even there. We'll just, you know, cover it up. How can I cover it up without erasing it? Just cover it up for just a second. So I'm just going to look at the rational function right here. And I'm going to think, do I have a horizontal asymptote? So the answer is, well, yeah, I have a horizontal asymptote because the degree of the top is smaller than the degree of the bottom. And when that happens, the horizontal asymptote is y equals 0. Now I'm going to think about the fact that this is a limit. Limits as x goes to infinity, that's just end behavior. And a horizontal asymptote is what happens on the end of your graph. Remember, you can cross a horizontal asymptote in between because the asymptote is just there for end behavior. So if the horizontal asymptote is y equals 0 and the x going to infinity is end behavior, then I'll be heading towards that horizontal asymptote when I'm on the right side of the graph. I could have taken the exact same function and thrown a negative infinity in front of here. The limit is still going to be heading to 0. Okay, so your turn with a rational function. So what's the limit as x heads to infinity of, say, negative 2x squared plus 3 over 3x squared minus 5? Okay, did you get it? Hopefully you did. We'll see. I mean, if you didn't, obviously you already know because you figured that out. Heading off to infinity, that's end behavior. This is just a rational function. I know that end behavior is really, do I have a horizontal asymptote or not? In this case, the horizontal asymptote would have been y equals negative 2/3 because that's the leading coefficient over the leading coefficient, which means that when I head to infinity, I am heading to the horizontal asymptote, and that's my limit. Okay, what about limit as x approaches negative infinity of, let's say, 5x minus 3x to the 4th over 2x squared plus 3x minus x to the 4th. All right, did you get it? If you didn't, maybe it's because things are in different orders. I am still looking at end behavior, even though I'm going to negative infinity. So end behavior is, and basically am I leveling off to a horizontal asymptote or not? Degree of the top and the bottom is the same. So the horizontal asymptote would have been y equals 3. Those are my leading coefficients, in which case that means that this limit is heading to the horizontal asymptote. Whether you're going to the left-hand side or the right-hand side, this limit would be heading to 3. Okay. Let's try the limit as x heads to infinity of, say, 2x squared over 1 minus x. Okay, so in this case, the degree of the top and the bottom are not the same, so it's not just going to be leading coefficients this time. Sorry, that 2 is messed up. The degree of the top is only bigger by 1. So I do know that there's no horizontal asymptote. If I was wanting to graph it, there would be a slant asymptote. So you would have a slant asymptote. However, even with a slant asymptote, like you're going to be heading off, you look back up here, you're going to be heading off to either a positive, and your y is going to keep getting bigger and bigger, and or your y's are going to keep getting smaller and smaller. They're not heading to a specific number. They are leveling off to a slanted line, but they're still not heading to a specific y value. So I'm just going to go ahead and say that this limit doesn't exist because that's the safest route. I mean, even if you're heading to infinity or negative infinity, does not exist is always an acceptable answer, and it's the preferred answer, honestly, in most textbooks. All right, well, we don't always deal with rational functions. That would be ideal, but we don't. So I just want to show you of a couple of, these are higher level, but I just want to see what you can make of it. Okay, limit as x heads to infinity of the square root of x squared minus 5 over 3x squared. All right, how'd you do? That one was just shot in the dark. So the reason why the limit comes out to 0, which you've now seen. The reason why is because if we're letting x get really, really big, and I think of that quote unquote, I'm doing the air quotes, you can't see me, that quote unquote plugging in infinity. This would have been infinity squared minus 5 square rooted over 3 times infinity squared. But that whole squaring thing, like the whole infinity, like just making it be infinity, you gotta really kind of like keep in mind that it's still kind of an infinity squared. I know it's a new infinity, but for right now, I'm gonna leave it like that. Now, when we get really, really, really big, this whole minus 5 right here thing, this does not really make a big deal. You plug in a really big number, you square it, you subtract 5, it's not making much of a difference in the infinite world. So it's almost like I can ignore this minus 5, which means that this kind of is just an infinity squared, square rooted, which means I kind of have a 3 over an infinity squared. So this is kind of like an infinity over 3 times an infinity squared. And again, these are kind of like just variables. So if this is just some number, I'll just put in an n for the number, over 3 times a number squared. Well, now the degree of that denominator is larger than the degree of that numerator. So when we head to infinity, the denominator is the thing that's going to be growing much, much faster than a number being squared and then square rooted. So that's why the limit is equal to 0. We can always check that on the calculator. So let's do that right quick. Oh no, I'm about to spill, about to spill. All right, let's check that on the calculator real quick just so you can kind of believe me. Where's my camera? Oh shoot, my calculator is over here. Okay. So that was, pause this for a second. Okay, sorry, I wanted to get it typed in there and get myself all situated. Okay, so this is the function that we're looking at. If I just want to assume standard window, remember that's a negative 10 to 10 on x's and y's, you would see that we would have that horizontal value there. Stuff happening in between and that horizontal value. We definitely can't plug in 0, so 0 is going to be a point of discontinuity because you can't divide by 0. And then we also have the square root in the numerator, so you can't take the square root of a negative number, so you do have to be careful. That's why there's some values missing in between, so the domain is not all reals. But you can see, like, if I wanted to use the table, remember, go to your table set and change your independent variable to ask. And then if you plugged in, you know, like, say, I don't know, a big number, like, say 10. Is 10 a big number? Or say 100. Or say 1,000, or say 1,000,000. So remember, this is scientific notation. So this means 0.00000 and then 3. This number is getting really, really close to 0. So just me using the calculator as another way to show that that limit is equal to 0. Okay. Let's do one more. Sorry, I'm like on my cord. Okay. Let's take the limit as x heads to negative infinity of 3x minus 5 over square root of 4x squared plus 1. All right, this one's a little tricky. So if you didn't get it right, again, I'm going to go with that whole quote unquote plugging in. So I'm going to have 3 times an infinity minus a 5 over the square root of 4 times an infinity squared plus a 1. Now remember, I'm really not, like, saying plug in infinity is really not mathematically correct. There's a lot, like, people who would probably not be happy with me saying that. But it's just to kind of get your mind thinking about this. So as I'm getting really, really big numbers, this whole plus 1 down here in the bottom, that doesn't really matter. I mean, even if it was like a plus 1,000, that's still not a large enough number in the infinite realm. Like, you got to think, these numbers are infinite. They are going forever and ever and ever. There's no end. That's just mind-blowing to think about. So there's no end. It's never going to stop. So this whole plus 1 thing really has no bearing. So really, I'm talking about now just a 3 times some number. Even this minus 5, who cares about that minus 5? It's really not making much of a difference. So really, you've got some number, big number, times 3. In the denominator, you've got some big number squared times 4 and then square rooted, because the whole plus 1 really isn't making that big of a deal. So your denominator is almost like 2 times a number. And now you're at the situation where it's like, oh, well, then these things kind of reduce out and you're left with a 3/2. However, remember I didn't plug in the right thing. We're going to negative infinity, aren't we? So we're really supposed to be going to negative infinity. But then I'm squaring that negative infinity. So me thinking of it like just a 4n squared is fine, but in the numerator, that should have been a negative 3n. So that's why this limit was going to negative 3/2. And again, if you want, you can, I mean, you guys are at home and you've got your calculator, just grab your calculator and check it out and see if it matches up. But next year, if you're going into calculus, this would be something that you'd have to evaluate without a calculator. Okay. Alrighty, I'm gonna sign off on this one. Hope you guys are doing well.